Right now, scattered across the observable universe, there are roughly 200 billion stars. If you tried to count them aloud, naming one every single second without ever stopping to sleep or eat or breathe, you would need more than 6,000 trillion years to finish. A span of time hundreds of thousands of times longer than the universe itself has existed. Each of those stars is a furnace. Each one pours light into the darkness in every direction, the same way our own sun floods the daytime sky until it drowns out everything behind it. And in an endless universe, filled evenly and forever with endless stars, there is no direction you could possibly look without your line of sight eventually landing on the glowing surface of one of them. The whole sky, in every direction, at every hour of the night, should be a solid wall of fire. And yet, when you walk outside tonight and tilt your head back, the space between the stars is not bright. It is black. It is the deepest, oldest darkness you will ever see. Here is what will quietly unravel everything you think you know about the night sky. That darkness should be impossible. The simple fact that it is dark up there, instead of blindingly, lethally bright, is one of the most profound clues the universe has ever offered about its own origin, its own age, and its own slow and certain death. If you enjoy slow, careful journeys through the largest questions in science, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. Get comfortable, make yourself warm. We are about to spend the next few hours inside a single question that took humanity 400 years to answer. Let's begin. The night sky has looked very much the same to human eyes for as long as there have been human eyes to look. For roughly 200,000 years, people glanced up at the darkness between the stars and felt nothing strange about it at all. The reason seemed obvious. The sun had set. The source of all that daytime brightness had slipped below the horizon, and so of course the world went dark. Night was simply the absence of the sun. Nobody thought there was a mystery here, because the explanation felt complete long before the question was ever asked. That intuition is perfectly correct about the sun, but it quietly hides something enormous. It assumes, without ever saying so, that the sun is the only object in the sky truly capable of lighting it up. And for most of human history, with nothing but the naked eye, that assumption seemed entirely reasonable. The stars were faint little points, beautiful but feeble, sprinkled thinly across a vast black canvas. The darkness was the canvas. The stars were a handful of scattered grains of light. The canvas was simply far, far bigger than the grains. Then the telescope arrived, and the canvas began to fill in. Every time someone built a larger instrument and pointed it at what looked like an empty patch of sky, that patch was not empty. It was full of stars too faint to see with the eye alone. Behind those stars were fainter stars. Behind the fainter stars were faint smudges that would one day turn out to be entire galaxies, each one holding hundreds of billions of suns of its own. The darkness, it turned out, was not a canvas at all. The darkness was a question. Every empty-looking gap was a place where the eye simply could not reach far enough, and the deeper anyone looked, the more light they found waiting in the black. This raised something that should have been deeply troubling, and for a long time almost nobody let it trouble them. If there are more stars the farther out you look, and if the universe goes on without end, then the supply of stars never runs out. Look in any direction, push your gaze out far enough, and there will always be another star somewhere along that line. Not most directions, every direction. The sky should have no gaps at all. One of the first people to truly stare into the size of this idea was an Englishman named Thomas Digges. In the year 1576, in London, Digges published a small work meant to explain the new sun-centered cosmos of Copernicus to English readers. Copernicus had moved the sun to the center and set the Earth in motion around it, but he had still kept the old picture of a finite outer shell of fixed stars, a kind of ceiling on the world. Digges did something bolder. He tore the ceiling off. In his diagram, the stars were not painted on a single sphere. They scattered outward in all directions, on and on, without any edge. He described a heaven that stretched up infinitely, filled with countless stars at every distance. It was a breathtaking vision, and it carried a poison inside it that Diggers himself never quite tasted. If the stars truly went on forever, then the night should not be dark. He had drawn an infinite sky of suns, and not noticed that such a sky could not possibly be black. The first person to feel the real weight of that contradiction was the German astronomer Johannes Kepler. In the year 1610, Kepler was reading the latest news from Italy, where Galileo had just turned his new telescope on the heavens and seen things no human had ever seen, including the fact that the soft glowing band of the Milky Way dissolved, under magnification, into uncountable individual stars. Kepler wrote a long, excited response to Galileo, and buried inside his enthusiasm was a sharp objection. If the universe were truly infinite, Kepler argued, and truly filled in every direction with stars like our sun, then the entire sky would shine as brightly as the sun itself. There would be no night. Since there obviously is a night, Kepler concluded that the universe could not be infinite. He believed there had to be a wall out there somewhere, a dark boundary enclosing all the stars, beyond which there was simply nothing. Kepler had found the paradox. He had stated it cleanly more than 4 centuries ago, and his solution was wrong, but it was wrong in a way that reveals exactly how powerful the puzzle is. Faced with a dark sky that should be bright, one of the sharpest minds in human history decided it was easier to put a wall around the entire universe than to accept that infinite stars could ever leave room for darkness. The darkness was that hard to explain. It bent great thinkers into strange shapes. The puzzle did not go away. It surfaced again roughly a century later, in London, in the hands of Edmund Halley, the astronomer whose name now belongs to a comet. Around the year 1720, Halley read 2 short papers to the Royal Society on the question of whether the stars could be infinite in number. He understood the difficulty. He understood that an endless field of stars threatened to fill the sky with light. His attempt at an answer leaned on the idea that the more distant stars were simply too faint to matter, that their light faded toward nothing with distance. But this is precisely where the human intuition fails, and it fails in a way that takes real care to see clearly. The light of a single star does grow fainter the farther away it sits. That part is true, but the number of stars at that distance grows at exactly the same rate that their brightness fades. The 2 effects do not partly cancel, they cancel completely. We will return to that perfect, deadly cancellation soon, because it sits at the very heart of the whole problem. The first person to do the arithmetic honestly was a young Swiss astronomer named Jean-Philippe Loider Chézeau. In the year 1744, working near Lausanne, de Chézeau was studying a bright comet, and in an appendix to his book about it, he laid out the star problem with real mathematical force. He pictured the universe as a series of nested shells centered on the Earth, like the layers of an onion drawn outward into space. He worked out how much light each shell would deliver, and he found that every shell, no matter how far away, delivered the same total amount of light to the Earth as every other shell. Add up enough shells, and the brightness climbs without limit. De Chézeau calculated that the sky should blaze far brighter than the sun. Not a little brighter, tens of thousands of times brighter, perhaps far more. A heaven of fire in which the sun itself would be a barely noticeable speck. Faced with his own terrifying result, de Chézeau reached for a way out. He proposed that space was not perfectly empty. Perhaps some thin fluid, some faint absorbing medium spread between the stars, soaked up a little of the light from each distant shell. Over enormous distances, he reasoned, this gentle absorption would add up and quietly swallow the light of the farthest stars before it ever reached us. The far shells would still be there, still pouring out their light, but a curtain of cosmic fog would dim them into darkness. It was an elegant idea. It was also wrong, and the reason it is wrong is one of the most beautiful arguments in all of physics. We will come to it. For now, hold on to the image of that fog, because someone far more famous was about to reach for the very same escape. That someone was the German physician and astronomer Heinrich Wilhelm Olbers. Olbers practiced medicine in the city of Bremen by day, tending to patients in the streets of a busy port town, and by night he climbed to a room at the top of his house that he had converted into an observatory, where he hunted comets and discovered asteroids until the early hours of the morning. He was one of the most respected observers of his age, and in the year 1823, Olbers published a short paper that restated the old puzzles so clearly and reached such a wide audience that the problem has carried his name ever since. We call it the dark night sky paradox, but more often we simply call it the paradox of Olbers. Olbers framed it with great clarity. In an infinite universe, evenly filled with stars, the sky everywhere should shine like the surface of the sun. He understood the shells. He understood the cancellation, and like de Chezeaux before him, whose work he may not have fully known, Olbers proposed that interstellar space must contain some faint absorbing matter, some thin haze that quietly drank the light of the most distant stars and kept the sky dark. It was the same fog, raised a second time, by a great mind reaching for the same comforting exit. Here is the argument that closes that exit forever, and it is worth slowing down for, because it is one of those rare ideas that feels obvious only after you have seen it, and impossible to unsee afterward. Imagine that thin absorbing fog really does exist between the stars. The light from distant suns strikes it. The fog absorbs that light. But absorbed light does not simply vanish. Energy is never destroyed. When matter absorbs light, it warms up, and anything that warms up begins to glow. This is not a special rule for cosmic fog. It is the same law that makes a poker glow orange in a fire and a stove element glow red when you leave it on. Pour enough light into any material, and it will heat until it shines as brightly as the source that is heating it. So picture the fog soaking up starlight for billions of years. It warms further. Eventually it reaches the same temperature as the stars themselves, and at that point it stops being a curtain and becomes a second source of light, glowing just as fiercely as the stars it was supposed to hide. The fog cannot save the darkness. Given enough time, the fog itself catches fire. There is no possible substance you can spread between the stars that will drink their light forever without eventually blazing in return. This is a direct consequence of the second law of thermodynamics, the deep principle that heat flows until everything reaches the same temperature, and it shuts the door on absorption completely. The darkness cannot be hidden behind a veil, because any veil thick enough to matter must in the end light up. So we are left exactly where Kepler stood 400 years ago, only with the easy answers stripped away. The geometry is sound. The stars really do grow more numerous with distance at the same rate their light fades. The fog does not work, because the fog would glow. The sky, by every reasonable assumption people held for centuries, should be an unbroken sheet of light as bright as the sun, in every direction, all night long. And it is not. It is dark. This distinction matters enormously, because the darkness above your head is not a small or local fact. It is not about clouds or city lights or the particular night you happen to step outside. It is a statement about the entire universe. A truly infinite, truly eternal, evenly filled cosmos is flatly contradicted by the plain experience of looking up and seeing black between the stars. Something in that picture must be false. One of the assumptions that felt too obvious to question, infinite stars, an unchanging universe, endless time, must be quietly, profoundly wrong. And so the darkness of the night sky stops being an absence and becomes something else entirely. It becomes evidence. It becomes a message written across the whole sky in a language that took 4 centuries and the combined work of physicists, astronomers, and one strange and visionary poet to finally learn to read. The darkness is not empty. The darkness is telling us something about how the universe began, how it is changing, and how it will end. For 400 years, almost no one understood what it was trying to say. Tonight, slowly and carefully, we are going to listen. To understand what the darkness is telling us, we first have to understand exactly why it should not exist, and that requires dismantling, carefully and completely, everything your eyes have quietly taught you to believe about looking up at night. The argument is not difficult. The mathematics behind it is in fact remarkably simple. Simple enough that a careful student could follow it on a single sheet of paper. That simplicity is part of what makes it so unsettling. The conclusion does not hide behind impossible equations. It walks straight up to you in plain arithmetic and tells you that the sky should be on fire. The whole paradox rests on a small number of assumptions, and for most of human history each of them seemed not merely reasonable, but obvious. There are 4. Hold them in your mind one at a time, because the entire mystery, and eventually its solution, lives inside these 4 quiet ideas. The first assumption is that the universe is infinite in size. It goes on forever in every direction, with no edge, no wall, no boundary of any kind. This is what Thomas Digges imagined, and what most thinkers came to accept. A finite universe with a wall raises an awkward question of its own, namely what lies on the other side of the wall, and so an endless cosmos felt cleaner, more natural, more in keeping with a creation without limits. The second assumption is that the universe is unchanging and eternal. It has always existed, more or less as it is now, and it always will. The stars have been shining forever. There was no beginning, no moment when the light switched on. This idea sat at the foundation of physics for centuries. A universe with a beginning seemed to demand an explanation for that beginning, and an eternal universe conveniently needed no such thing. Even the greatest minds preferred it. We will see much later just how stubbornly that preference held on. The third assumption is that the stars are spread out roughly evenly. Not perfectly, of course. Stars cluster into galaxies, galaxies gather into groups and clusters. But step back far enough, the thinking went, and the lumps smooth out, and the universe looks much the same everywhere, with about the same density of stars in any large region you might choose. There is no special place, no center, no thinning out toward the edges, because there are no edges. The fourth assumption is the most invisible of all, because it describes the behavior of light itself. It is the assumption that light, once emitted by a star, travels outward in a straight line forever, growing fainter with distance in the ordinary way, but never disappearing, never losing its color, never being stopped except by running into something solid like another star. Light, in this picture, is a faithful, tireless messenger. Send it across 1 billion years of empty space, and it arrives unchanged in every way except dimmer. Take those 4 assumptions together, and the disaster follows with cold certainty. To see exactly how, picture the universe the way Deschaud did, as a set of nested shells centered on you, the observer, standing on the Earth. Imagine the nearest shell as a thin spherical layer of space surrounding you, perhaps 1 light year thick, beginning a fixed distance away. Then a second shell of the same thickness just beyond it. Then a third, and a fourth, marching outward into the dark, each one a hollow sphere wrapped around the last, like the rings inside a tree trunk drawn out into 3 dimensions. Now consider a single shell, far out in space, and ask 2 questions about it. First, how bright does each star in that shell appear from where you stand? The answer is governed by one of the most reliable rules in all of physics. The apparent brightness of a light source falls off as the square of its distance. Move a star twice as far away, and it appears 1/4 as bright. Move it 10 times as far, and it appears 1/100th as bright. This is the inverse square law, and it is simply a statement about geometry. Light spreads out over the surface of an expanding sphere, and the area of that sphere grows as the square of its radius, so the light thins out at exactly that rate. The second question is this: how many stars are in that distant shell? Here is where the trap snaps shut. The shell is a thin spherical layer, and the amount of space inside it, its volume, is its surface area multiplied by its thickness. The surface area of a sphere also grows as the square of its radius. So a shell twice as far away has 4 times the surface area, and therefore 4 times the volume, and therefore if the stars are spread evenly, 4 times as many stars. Now place those two answers side by side and watch what happens. The stars in the more distant shell are each 1/4 as bright, but there are 4 times as many of them. The dimming and the multiplying are governed by the very same power of distance, the square, and so they cancel each other perfectly. Each shell, near or far, contributes exactly the same total amount of light to your sky. Not approximately the same, identically the same. The faintness of distance is precisely balanced by the abundance of distance, in a cancellation so clean it almost feels designed to torment us. Consider what this means. If every shell delivers the same light, and the universe is infinite so the shells never run out, then you are adding up an endless line of equal contributions. The first shell adds a certain brightness, the second adds the same, the 1,000th adds the same. The shell a trillion light years away adds the same again. An infinite sum of equal, non-zero amounts has no limit. The total brightness of the sky climbs forever, toward infinity. Now in reality the brightness does not literally become infinite, and the reason why is even more vivid than the shells. It is because nearer stars block your view of farther ones. Stars are not transparent. A star directly in your line of sight hides everything behind it. So instead of imagining brightness adding up without limit, picture it this way. Send out a single line of sight from your eye in any direction at all. Follow it outward through the endless universe. In a cosmos packed forever with stars, that line cannot travel indefinitely through empty space. Sooner or later, near or far, it must strike the glowing surface of some star. It has to. There is no gap large enough to escape through, because beyond every gap lies another layer of stars, and beyond that, another, forever. This is the strange and total reality of an infinite, eternal, star-filled universe. Every single line of sight, every direction you could possibly point your eye, ends on the surface of a star. And the surface of a star is blazing bright. So the entire sky, every point of it, should glow with the surface brightness of a typical star. The dark gaps between the stars that you see on a clear night should not exist at all. Where you see black, there should be the surface of a distant sun, just one whose individual disk is too small to make out, blended seamlessly into its neighbours until the whole dome of the sky is one continuous sheet of stellar fire. To feel this in your body rather than only in your arithmetic, step out of space for a moment and walk into a forest. Imagine standing among the trees in a woodland so vast it has no edge, stretching unbroken in every direction for as far as the idea can carry you. Look straight ahead at eye level. Your gaze travels between the nearest trunks, slips past them, and continues into the depth of the forest. But it does not continue forever. Somewhere out there your line of sight meets a trunk and stops. Now look slightly to the left. Again your gaze threads between near trees, reaches deeper, and lands on a more distant trunk. Every direction you look, no matter how carefully you aim between the closest trunks, your eye eventually finds bark. In a truly endless forest, there are no gaps to the horizon. You do not see daylight through the trees. You see a solid, unbroken wall of wood in every direction, because the depth of the forest swallows every line of sight before it can escape. The night sky, under the old assumptions, is exactly that forest, except the trunks are suns, and the bark glows like the surface of a star. There should be no escaping line of sight. There should be no darkness. There should be a wall of light. This is why the darkness is a genuine paradox and not merely a curiosity, and here it is worth pausing to clear away the answer almost everyone reaches for first. Ask any person on the street why the night sky is dark, and they will tell you, without a flicker of hesitation, that it is dark because the sun has set. The sun is the source of light. At night the earth has turned away from it, The sun is hidden below the horizon, and so there is nothing left to light the sky. The answer feels airtight. It is delivered with total confidence. That confident answer is not exactly wrong. It is incomplete, and it is incomplete in a way that hides the entire mystery. Yes, our sun has set. But our sun is not the only sun. It is one ordinary star among that 200 billion trillion, and every one of those other stars is somewhere shining right now. The question is not why our own sun fails to light the night. The real question, the one that should keep you awake, is why all the other suns fail to do it. Why, when you look into the gap between two visible stars, is there not a more distant star filling that gap, and behind it another, and another, all the way out, until the gap itself glows? The setting of our sun explains the absence of daylight. It does nothing whatever to explain the presence of darkness in an infinite field of other stars. The reason the misconception is so durable is that it works perfectly well at human scale. In ordinary life, when a light source is removed, darkness follows, and that is the whole story. Our entire intuition about light and dark is built inside a small, well-lit world of rooms and lamps and a single dominant sun. We learn, correctly, that turning off the source brings the dark. Nobody in daily life ever has to reckon with an infinite supply of light sources stretching away forever in every direction. So nobody develops the instinct to ask what such a thing would look like. The paradox lives in a regime our intuition was never built to handle, and so our intuition hands us a comfortable answer and quietly walks away from the real problem. Rebuild the picture from the ground up, and the true shape of the question appears. The darkness of the night sky is not the absence of one light source. It is the failure of infinitely many light sources to fill the sky, when by every reasonable calculation they should. The mystery is not that it is dark after the sun goes down. The mystery is that it is dark at all, given how many other suns there are and how endless the universe was assumed to be. And consider, finally, what it would actually mean if the old assumptions were true and the sky did blaze. This is not a gentle, decorative kind of brightness we are talking about. If every point of the sky shone with the surface brightness of the sun, then standing under the night sky would be like standing inside an oven whose walls were the surface of a star, on every side, with no shadow and no escape. The temperature of the Earth's surface is set by a balance between the sunlight it receives and the heat it radiates away. Replace the small disk of a single sun with an entire sky of stellar surface, and that balance shatters. The oceans would not merely warm, they would boil away into vapor in moments. The rocks would soften and run. The atmosphere would be stripped off into space. Nothing made of ordinary matter could survive beneath a sky like that, because the sky itself would be as hot as the face of the sun, in every direction at once. So here is the quiet, staggering truth that the old physics could not absorb. The darkness of the night sky is not a backdrop against which life happens to take place. The darkness is the reason life is possible at all. If the universe were the simple, infinite, eternal thing that even Kepler and Olbers assumed, you would not be lying in a dark room listening to these words, because there would be no dark room, no cool night air, no liquid water, no earth, no you. The blackness overhead, the very thing that for thousands of years seemed too ordinary to question, is a sign that the universe is not what it appears to be, and that whatever it truly is, it has left exactly enough room in the dark for us to exist inside it. So one of the four assumptions has to be false. The geometry leaves no room to wriggle out. If the sky is dark, and we know with our own eyes that it is, then the universe cannot be all four things at once. It cannot be infinite in size, and eternal and unchanging, and evenly filled with stars, and perfectly transparent to light, all at the same time. At least one of those quiet foundations has to crack. The work of the next part of our story is the work of a detective standing over four suspects, examining each one in turn, asking which of them could possibly be guilty of the darkness. And as with any careful investigation, we begin by ruling out the answers that feel most comfortable. The first suspect is the assumption that stars are spread out evenly. Perhaps you might think, the stars are not smooth at all. We can see with our own telescopes that they are not. Stars gather into galaxies. Galaxies cluster into groups. Groups assemble into superclusters, and between these great islands of light stretch enormous voids of nearly empty space. Regions hundreds of millions of light years across in which there is almost nothing at all. Maybe, the thought goes, the universe is lumpy all the way up, clumps within clumps within clumps, with the empty voids growing larger and emptier at every scale. If that were true, then most lines of sight would slip out through the gaps and travel forever through emptiness, without ever striking a star. The darkness would be the view down those endless corridors of void. This is not a foolish idea. In the early 20th century, a thoughtful Swedish astronomer named Carl Charlier worked out the mathematics of exactly this kind of universe. A hierarchical cosmos of clusters, nested inside larger clusters without end. And he showed something genuinely interesting. If the clumping is severe enough, if the voids grow large enough at each level of the hierarchy, then the total light reaching us really can stay finite. The darkness can survive, in principle, inside a sufficiently lumpy infinite universe. For a time this looked like it might be the answer. The structure we actually see in the sky, the clusters and the voids, seemed to be doing exactly the job the paradox required. But the universe, when we measure it carefully, refuses to cooperate with this rescue. The clumping is real, and it is dramatic, but only up to a point. As we survey larger and larger volumes of space, the lumps do not keep growing without limit. They smooth out. Beyond a scale of a few 100 million light years, the universe becomes remarkably uniform. The same density of galaxies in this enormous region as in that one. The great voids and great walls of galaxies averaging away into a smooth and even glow. The cosmos is lumpy at the scale of galaxies and clusters, but it is smooth at the largest scales, and a universe that becomes smooth at large scales cannot hide behind its own clumpiness. The first suspect, uneven distribution, can dim the sky a little. It cannot make it dark. We set this suspect aside, guilty perhaps of a small contribution, but not of the crime itself. The second suspect is the one that tempted both de Chezaux and Olbers, the idea that something in space absorbs the light of the distant stars. We have already met the argument that destroys it, but it is worth standing in front of one more time, because it is one of the cleanest pieces of reasoning in all of science, and because it teaches us something we will need later. Suppose space is filled with some thin material, dust or gas or any substance you like, and suppose it soaks up the light from the farthest stars before that light can reach us. The trouble is what happens to the energy it absorbs. Energy does not disappear when it is absorbed. It turns into heat. The absorbing material warms up, and as it warms it begins to radiate light of its own. Pour starlight into it for long enough, across the unimaginable stretches of an eternal universe, and the material climbs in temperature until it glows exactly as brightly as the stars heating it. At that point, the curtain is no longer a curtain. It is itself a wall of light. The absorber cannot win, because in an infinitely old universe, everything that absorbs light forever must eventually reach the same temperature as the light and shine in return. This is the second law of thermodynamics, speaking with absolute authority. Heat flows from hot to cold until the difference is gone, and a cold absorbing fog bathed forever in starlight cannot stay cold. The second suspect is innocent. Absorption is not what saves the night. There was a third idea, subtler than the others, that lingered for many years. What if the light from distant stars does not get absorbed, but simply grows tired? What if over vast distances, light slowly loses energy on its own, fading and reddening as it travels, until the most distant starlight drains away to nothing? This notion even acquired a name. It was called tired light, and on the surface it seems to offer a way out. If the farthest light loses its energy before it arrives, the far shells go dark and the sky can stay black. but tired light fails for reasons both theoretical and observed. There is no known mechanism by which light traveling through empty space simply leaks away its energy without being scattered or absorbed by something, and any such scattering would blur the distant universe into a smear, which we do not see. The crisp, sharp images we capture of galaxies billions of light years away would be impossible if their light had been gradually bled of energy along the way. The third suspect, like the others, does not hold up under questioning. And so, one by one, the comfortable answers fall. The stars are smooth enough at large scales to fill the sky. Nothing absorbs the distant light without eventually glowing. Light does not quietly tire and fade on its own. 3 of our 4 suspects have alibis, which leaves us standing before the 2 assumptions we have not yet seriously challenged, and they are the 2 that felt the most untouchable of all: that the universe is infinite in extent, and that it is eternal and unchanging, with stars that have been shining forever. Here is where the investigation turns, and where, if you are listening closely, a quiet sense of unease should begin to gather. Because the way out of the paradox is not going to be a small correction. It is not going to be a clever adjustment to the density of stars or the properties of dust. The way out is going to require throwing away one of the deepest beliefs that thinkers held for thousands of years about the nature of reality itself. The way out is going to require accepting that the universe has not been here forever. The first person to grasp the true escape with quantitative force was the Scottish physicist William Thomson, known to the world by his title, Lord Kelvin. In the year 1901, near the end of a long and towering career at the University of Glasgow, Kelvin returned to the old paradox of the dark sky and did something none of his predecessors had managed. He calculated, with real numbers, just how far out into space the stars would have to extend, and for just how long they would have to shine in order to fill the sky with light. And his answer was devastating to the old picture. For the sky to blaze as the simple paradox demanded, you would need stars stretching out to such an enormous distance that the light from the farthest of them would take an almost unimaginable span of time to reach us, far longer than any star can actually shine before exhausting its fuel, and far longer than the universe could plausibly have existed. This was the crucial new ingredient, and it had been hiding in plain sight the whole time. Stars are not eternal. They burn through their fuel and die. Our own sun has been shining for about 4.5 billion years, and is roughly that long again before it swells, sheds its outer layers, and fades into a cooling ember. A star cannot pour out light forever, because no star has an infinite tank of fuel. And here is the second ingredient, the one that ties everything together. Light does not travel instantly. It moves at a fixed and finite speed, fast beyond ordinary comprehension, but finite all the same. Which means that when you look at a distant star, you are not seeing it as it is now. You are seeing the light that left it long ago. Light that has been crossing the dark for years or centuries or millions of years to reach your eye tonight. Combine those 2 facts, and the darkness begins, at last, to make sense. If stars have only been shining for a finite time, and if their light travels at a finite speed, then there is a limit to how far away a star can be, and still have its light reach us. Beyond a certain distance, the light simply has not arrived yet. It is still on its way, still crossing the gulf, and the gap in the sky where that distant light should be is dark, not because there is no star there, but because the news of that star has not yet had time to travel across the universe to your eye. The dark gaps are not empty. They are unfinished. They are places where the light is still in transit. There is something almost unbearably poignant in this, and the person who felt it first was not a physicist at all. He was a poet. In the year 1848, in the city of New York, the writer Edgar Allan Poe, near the end of his troubled life, delivered a strange and sprawling lecture that he later published as a prose poem he titled Eureka. It was a sweeping attempt to describe the entire universe, its origin, its structure, and its fate, written not as science but as a kind of cosmic vision. And buried inside it, Decades before the physics existed to support it, Poe stated the resolution of the dark sky paradox with stunning clarity. He reasoned that the reason we see voids and gaps between the stars, rather than an unbroken blaze, is that the distance to the farthest background of stars is so immense that the light from it has not yet had time to reach us at all. The gaps are dark, Poe wrote in his own words, because their light has simply not arrived. Sit with that for a moment. A poet, working from intuition and imagination, with no telescope capable of proving it, and no theory of an expanding universe to lean on, looked up at the dark gaps in the sky and understood that they were a measure of time. He understood that the darkness was telling us the universe had not always been, that there was a beginning, and that we can only see as far out into space as light has been able to travel since that beginning. The astronomers of his age largely ignored Eureka as the eccentric musing of a literary man. They should not have. He had seen, through the eye of a poet, the very thing that the eye of physics would take another century to confirm. This is the strange reality the darkness was always pointing toward. The night sky is dark, in part, because the universe is not infinitely old. There was a first moment, and because light needs time to travel, we can only ever see the portion of the universe whose light has had time to reach us since that first moment, a finite bubble of visibility surrounding us in every direction, with a hard edge set not by any wall in space, but by the age of time itself. Outside that bubble, there may be more universe, perhaps infinitely more, but its light has not arrived, and so to us it is simply dark. And yet, this is only half of the answer. The finite age of the universe explains why the supply of visible stars runs out, why the shells do not go on forever, why there are dark gaps where the light has not yet come. But it does not, by itself, fully explain why the gaps are so very dark, so completely and utterly black, rather than merely dimmer than they would be in an eternal cosmos. To understand the full depth of the darkness, we need the second great discovery of the 20th century, a discovery that revealed the universe is not merely finite in age, but is doing something that no one before the 20th century had ever imagined. The universe is not standing still, it is growing, and the growing itself is reaching into the light of distant stars and quietly stealing it away. Begin with the simplest and strangest fact about light, the one that makes the night sky into a kind of time machine. Light travels at a fixed speed, roughly 186,000 miles in a single second, fast enough to circle the Earth more than 7 times between one heartbeat and the next. At human scale, this is effectively instant. Flip a switch and the room fills with light before you can register any delay. But the universe is not built to human scale, and across cosmic distances the finiteness of that speed changes everything. When you look at the sun, you are not seeing it as it is. You are seeing light that left its surface about 8 minutes ago. If the sun were somehow snuffed out this instant, you would carry on in full daylight for those 8 minutes, utterly unaware, until the darkness finally arrived. Look further out and the delay grows. The light from the nearest star beyond our sun, Proxima Centauri, has been travelling for a little over 4 years before it reaches your eye, which means you see that star not as it is tonight, but as it was 4 years ago. The light from the great galaxy in Andromeda, the most distant object the unaided human eye can see, set out on its journey about 2.5 million years ago, when our own ancestors were just beginning to shape the first stone tools. That faint smudge in the autumn sky is an image 2.5 million years old, a photograph of a galaxy as it looked before there were any humans to photograph it. This is the profound reality that the finite speed of light forces upon us. To look out into space is to look back into time. There is no way to see any distant thing as it is now. We can only ever see the past, and the further away we look, the deeper into the past we see. The most distant galaxies our greatest telescopes can detect appear to us as they were more than 13 billion years ago, in the youth of the cosmos, their ancient light only now completing a journey that began when the universe itself was new. Now follow that idea to its edge. If looking farther means looking further back in time, then there must be a limit to how far we can look, set not by the power of our telescopes but by the age of the universe. We cannot see anything whose light would have needed more time to reach us than the universe has existed, because that light has not arrived yet. There is a sphere surrounding us, centered on the Earth only because the Earth is where we happen to stand, beyond which we simply cannot see. Astronomers call it the observable universe. Its boundary is not a wall. There is no barrier out there, nothing solid, nothing you could ever travel to and touch. It is a horizon made of time. It marks the distance light has been able to travel since the beginning. And just as a ship sailing toward the horizon never reaches the line where sea meets sky, no traveler could ever reach the edge of the observable universe, because it is not a place. It is the limit of how far back our vision can reach. This single idea, that the universe has a finite age and therefore a finite visible horizon, already begins to dissolve the paradox. The shells of stars do not march outward forever after all. They stop, not because the universe stops, but because beyond a certain distance the light has not yet had time to come. The endless wall of fire that the old assumptions demanded was always built on the belief that we could see stars at every distance, out to infinity. We cannot. We can only see out to the horizon of time, and within that finite bubble there are only so many stars, only so much light, with vast dark gaps where the light of more distant things is still crossing the void, or where there were no stars yet because the universe was too young to have made them. But how did anyone discover that the universe has an age at all, when for thousands of years the wisest thinkers assumed it had simply always been? The answer came in stages, through a handful of patient people staring at faint smudges of light, and it ranks among the greatest detective stories in the history of human thought. It began, quietly and without much recognition at the time, with a woman named Henrietta Swan Leavitt. In the early years of the 20th century, Leavitt worked at the Harvard College Observatory in Massachusetts as one of a group of women hired to do the painstaking labor of measuring the brightness of stars on photographic plates. They were called computers, because computing was their job, performed by hand, plate after plate, for very little pay and even less credit. Leavitt was assigned to study a particular kind of star that pulses, brightening and dimming in a steady rhythm over days or weeks. These are called Cepheid variables, and in studying hundreds of them, Leavitt noticed something that would unlock the size of the cosmos. The brighter a Cepheid truly was, the slower it pulsed. The rhythm of the star revealed its true brightness, with beautiful precision. This was the key that astronomy had been missing for centuries. If you know how bright a star truly is, and you measure how bright it appears, the difference tells you exactly how far away it must be, because of that same inverse square law of dimming. A faint-looking Cepheid with a slow pulse must be far away. Leavitt had handed astronomers a measuring tape long enough to reach across the universe. She herself was given little credit in her lifetime, and she died before the full power of her discovery was widely understood. But every measurement of cosmic distance made since rests on the foundation she laid, plate by plate, in a Harvard workroom. With that measuring tape in hand, others began to reach outward. At the Lowell Observatory in Flagstaff, Arizona, an astronomer named Vesto Slipher spent years in the 1910s studying the faint spiral smudges then called nebulae, splitting their light into its component colors to read the signatures hidden there. And he found something puzzling. The light from nearly all of these spirals was shifted toward the red end of the spectrum, stretched to longer wavelengths, in the manner of a source rushing away. Almost every spiral he measured seemed to be fleeing from us, and many of them at tremendous speed. Slipher did not know what to make of it. Nobody yet knew that these spirals were entire galaxies, vast and distant, far beyond our own. The person who put the pieces together was the American astronomer Edwin Hubble, working at the Mount Wilson Observatory in the mountains above Los Angeles, with the most powerful telescope in the world at the time, a giant whose main mirror measured 100 inches across. In the early 1920s, Hubble found Cepheid variables inside the Andromeda spiral, used Leavitt's relation to measure their distance, and proved beyond argument that Andromeda was not a cloud within our own galaxy at all. It was a separate galaxy, an island of hundreds of billions of stars, unimaginably far away. In a single stroke, the universe became enormously larger than anyone had believed. Our own Milky Way was revealed to be just one galaxy among countless others, scattered through a cosmos far vaster than the old imagination could hold. Then, Hubble took the final step, the one that changed everything. He combined the distances he was measuring to these galaxies with the redshifts that Slipher and others had recorded, and in the year 1929, he announced a relationship so simple and so shocking that it reshaped our entire conception of reality. The farther away a galaxy was, the faster it was rushing away from us. A galaxy twice as distant fled twice as fast. A galaxy 10 times as distant fled 10 times as fast. The recession speed was directly proportional to the distance, a clean straight line running across his data. Consider what this means, because at first it sounds as though it places us at the center of some great cosmic repulsion, as if all the galaxies were fleeing from us in particular. They are not. The deeper truth is far stranger and far more beautiful. It is not that the galaxies are flying apart through space. It is that space itself is expanding, swelling, stretching in every direction, and carrying the galaxies along with it like marks on the surface of something growing. To feel how this works, imagine a loaf of raisin bread dough set out to rise. The raisins are scattered through the dough, and as the dough expands, every raisin moves away from every other raisin. Pick any single raisin and call it home. From that raisin's point of view, all the other raisins are receding, and the ones that started farther away recede faster, because there is more expanding dough between them and you. This happens for every raisin equally. No raisin is the center. The center is everywhere and nowhere. There is no special raisin that the others flee from. They all flee from each other, simply because the dough between them is growing. This distinction matters enormously, and it is one of the most commonly misunderstood ideas in all of cosmology. The galaxies are not moving outward through a fixed and empty space, like debris hurled from an explosion. The space between them is itself being created, stretching, growing, so that two galaxies sitting perfectly still relative to their local surroundings nonetheless find the distance between them widening year after year, because new space is welling up in the gap between them. The cosmos is not expanding into anything. It is not a balloon inflating into a room. There is no outside. The expansion is the stretching of the very fabric within which everything exists. This was a conclusion so radical that even Albert Einstein resisted it. Years earlier, when Einstein had first applied his theory of gravity to the universe as a whole, his equations had told him plainly that the universe should be either expanding or contracting, that it could not sit still. He did not believe it. Like nearly everyone else, Einstein was certain the universe was eternal and unchanging, and so he inserted into his equations an extra term, a fudge factor, designed specifically to hold the universe still, to balance gravity and keep the cosmos frozen in place. He called it the cosmological constant. When Hubble's observations later revealed that the universe was in fact expanding, exactly as the original equations had insisted before he tampered with them, Einstein reportedly called that insertion the greatest blunder of his life. He had been handed the discovery of the expanding universe by his own mathematics, and he had refused to accept the gift. There was one person who did accept it, ahead of everyone else. A Belgian named Georges Lemaitre, a Catholic priest and a trained physicist, had worked out from Einstein's equations 2 years before Hubble's announcement that the universe must be expanding, and he had even estimated the rate. But Lemaitre went further than anyone. He reasoned that if the universe is expanding now, growing larger with every passing year, then in the past it must have been smaller. And if you run that film backward far enough, rewinding the expansion, all the matter and energy in the cosmos draws together, denser and hotter, until at the very beginning everything that now fills the universe was compressed into a single, unimaginably dense and hot state. Lemaitre called it the primeval atom. We know it today by a name that began as a mocking joke from a skeptic and stuck because it was unforgettable. We call it the Big Bang. And here it is essential to clear away the most stubborn misconception of all, because the name itself is misleading. The Big Bang was not an explosion that took place at some particular point in a pre-existing emptiness, hurling matter outward into a waiting void. There was no waiting void. There was no point in space where it happened, because space itself did not yet exist as a stage on which it could happen. The Big Bang was the beginning of space and time together. It did not happen at a place. It happened everywhere, all at once, because everywhere was the same place, all of existence compressed into that single hot dense state. When we say the universe is expanding, we do not mean that its contents are flying away from the site of an ancient blast. We mean that every part of space is stretching away from every other part, that the universe is growing larger from the inside, that the distance between any 2 points is increasing, with no center and no edge and no outside for any of it to expand into. This is the universe the darkness was pointing to all along. Not infinite and eternal, but finite in age, born from a hot, dense beginning roughly 13.8 billion years ago, expanding ever since. A universe with a first moment. A universe in which there has only been time enough for light to travel a certain distance, defining a horizon beyond which we cannot see. The dark gaps in the night sky are, in part, simply the places where we are looking back toward that beginning, toward a time before the stars in that direction had formed, or toward distances so great that even light, the fastest thing there is, has not finished crossing the gulf since time itself began. When you stare into the darkness between the stars, you are staring, in a real and literal sense, toward the edge of time. The black is not empty, it is the past, and at its very deepest, it is the dark that came before there was any light at all. The finite age of the universe takes us a long way toward the darkness, but it is not the whole of it. If the only thing happening were a horizon in time, you might still expect the gaps between the stars to glow softly with the light of the early universe, dimmer than Olbers feared, but not perfectly, utterly black. Yet the gaps are black, profoundly and completely black, and to understand that final depth of darkness we need to follow what the expansion of space does not just to the positions of galaxies, but to the light itself as it crosses the growing void. Because the expansion does something quietly astonishing to every ray of light that travels through it. It stretches it, and in stretching it, it drains its color, its energy, and its power to light the sky. Picture a single wave of light leaving a distant galaxy billions of years ago. Light is a wave, with crests and troughs, and the distance from one crest to the next is its wavelength. That wavelength is what determines its color. Short wavelengths look blue and violet to our eyes. Longer wavelengths look red. Stretch the wavelength longer still, and the light passes beyond red into the infrared, invisible to the eye but felt as heat. Stretch it further, and it becomes microwave radiation, and further still, radio waves, with wavelengths that can run for centimeters or meters or more. The color of light is simply the length of its wave. Now send that wave across an expanding universe. As it travels, the space it is moving through is itself stretching, growing larger in every direction. And the light wave, riding through that growing space, is stretched right along with it. The crests are pulled farther apart. The wavelength lengthens. By the time the light arrives at your telescope, after billions of years of crossing space that has been expanding the entire way, its wavelength is far longer than it was when it set out. Light that left its source as visible blue or white can arrive shifted toward the red, or pushed entirely out of the visible range into the infrared and beyond. This stretching is what astronomers call the cosmological redshift, and it is the second great mechanism that keeps the night sky dark. It is essential to understand that this is not the ordinary kind of redshift you may have heard of, the kind produced by motion. When an ambulance races past you, the pitch of its siren drops as it recedes, because each successive sound wave is emitted from a little farther away, and the waves are stretched out behind it. Light does something similar when a source moves away from you through space, and this is the Doppler effect. But the cosmological redshift is something deeper and stranger than that. The distant galaxies are not, for the most part, rushing away through space like an ambulance down a street. They are sitting more or less still in their own local patch of the cosmos. It is the space between you and them that is expanding, and as that space grows, it carries the light wave with it and stretches it from within. The wave is not being stretched because its source is fleeing. The wave is being stretched because the very medium it travels through is growing larger beneath it while it is in flight. This distinction matters enormously, and the cleanest way to feel it is to imagine drawing a wave onto a long strip of soft elastic. Take a rubber band, stretched out straight, and with a marker draw a series of evenly spaced ripples along its length. Crest and trough, crest and trough. Now grip both ends and pull. As the rubber stretches, every ripple you drew stretches with it. The crests move farther apart. The wave you drew grows longer, not because anything is moving along the rubber, but because the rubber itself, the thing the wave is drawn upon, is expanding. A wave of light crossing the expanding universe is exactly that ripple drawn on the stretching elastic. Space is the rubber, the light is the wave, and as space expands across billions of years, the light it carries is drawn out longer and longer, redder and redder, until the most ancient light of all arrives, stretched almost beyond recognition. Here is why this drains the sky of brightness, and not merely its color. The energy carried by light is bound up with its wavelength. Short, tightly packed waves carry more energy. Long, stretched out waves carry less. This is a fundamental property of light, as reliable as anything in physics. So when the expansion of the universe stretches a light wave to a longer wavelength, it does not merely change the color of that light, it lowers its energy. The light arrives carrying less power than it left with, and the farther the light has traveled, the longer it has been crossing the expanding void, the more it has been stretched, and the more energy it has lost along the way. The most distant light, from the earliest times, arrives the most stretched, the most reddened, and the most drained of all. Consider what this does to the old paradox. The geometry told us that distant shells of stars contribute as much light as near ones, because the dimming of distance is exactly balanced by the multiplying of stars. But that perfect cancellation assumed light arrives unchanged, only fainter. The expanding universe breaks the cancellation. Now the light from the most distant shells does not merely spread thin, it is stretched out, robbed of energy, shifted out of the visible band entirely. A distant shell that should, by pure geometry, have contributed its full share of visible brightness instead, delivers light so reddened and so weakened that your eye cannot register it at all. The expansion reaches into the farthest reaches of the sky and quietly turns down the light, shifting it into colors we cannot see and energies too faint to matter, leaving the gaps dark. Now extend that perspective across the full depth of the observable universe, and the effect grows more extreme the farther you look. Nearby galaxies show a gentle redshift, their light only slightly reddened. More distant galaxies show a stronger shift, their wavelengths noticeably stretched. The most distant galaxies and quasars our telescopes can detect have redshifts so large that light which left them as ultraviolet, with very short wavelengths, arrives stretched all the way into the infrared, its wavelength multiplied many times over by the expansion it has endured, and the speed of recession grows with distance in the same way. The nearby galaxies drift away slowly, the distant ones recede faster, and beyond a certain enormous distance, the galaxies are receding from us faster than the speed of light itself. That last statement deserves a careful pause, because it sounds like a violation of the most famous rule in all of physics, the rule that nothing can travel faster than light. But there is no violation here, and the reason is subtle and beautiful. Nothing is moving through space faster than light. The distant galaxies are barely moving through their local space at all. What is happening is that space itself is expanding, and at great distances there is so much space between us and a faraway galaxy, all of it stretching at once, that the total rate at which the gap widens can exceed the speed of light. The cosmic speed limit governs how fast anything can move through space. It places no limit on how fast space itself can grow, and so the most distant galaxies recede superluminally, not because they are racing anywhere, but because the ocean of space between us and them is swelling faster than light can cross it. This has a haunting consequence. If the space between us and a distant galaxy is growing faster than light can travel across it, then any light that galaxy emits toward us today can never reach us. It sets out in our direction, but the space ahead of it expands faster than it can advance, like a swimmer striking out for a shore that is receding faster than they can swim. There is, in other words, not only a horizon marking how far we can see into the past, but another kind of horizon marking the boundary beyond which events happening now can never reach us at all, no matter how long we wait. The universe is full of galaxies whose present light will never touch us, whose stories from this moment forward are forever sealed away behind the expansion of space. The darkness then is not only the past we cannot yet see, it is also, at its outermost edge, a future we will never receive. So the night sky is dark for two reasons working together, two great mechanisms braided into a single blackness. The first is the finite age of the universe, which gives us only a limited bubble of visibility, cutting off the supply of distant stars at a horizon set by the age of time. The second is the expansion of space, which stretches the light that does manage to cross the void, draining its energy and shifting it out of the visible range, so that even the light which reaches us from the deepest distances arrives too reddened and too faint to brighten the sky. Take away either one, and the darkness would be incomplete. Together they account for the black between the stars. And yet, even now, we have not reached the strangest part of the answer, because Olbers and Kepler were not entirely wrong. They imagined a sky filled in every direction with the surface of glowing matter, a uniform wall of light surrounding us on all sides. And here is the thing that ought to send a quiet shiver through you as you lie there in the dark. That wall exists. It is real. It surrounds us right now, in every direction, exactly as they imagined, a sphere of uniform glowing matter wrapped around the entire sky. The blazing wall that the paradox demanded is genuinely there. We have detected it. We have measured its temperature. We have photographed it across the whole sky. You cannot see it with your eyes only because the expansion of the universe has stretched its light so far that it has fallen out of the visible spectrum entirely, cooled and reddened across nearly 14 billion years, until what was once a blinding glow has become something invisible, something silent, something that fills the cosmos and passes through your body in this very moment, without your ever knowing it is there. The wall of fire that Olbers expected to find when he looked up at the night was always there. It was simply waiting, stretched into darkness, for someone to build an instrument that could finally reveal it. And when that revelation came, in the most accidental and almost comic way imaginable, it would confirm the birth of the universe and turn the dark night sky into the strongest evidence we have ever found that everything, all of it, had a beginning. To understand the wall of light that surrounds us, we have to travel back almost to the very beginning, to a time when the universe was unimaginably different from the cold, dark, spacious place we know tonight. In its first moments, the cosmos was not dark at all. It was a furnace. Everything that now exists, every galaxy, every star, every atom in your body, was compressed into a space far smaller and hotter and denser than anything we can truly picture. And in that early furnace, the universe was filled uniformly with blinding light. But here is the crucial thing. In those early times, you could not have seen that light, not because it was faint, but because the universe was opaque. It was so hot and so dense that light could not travel freely through it at all. To picture why, imagine the interior of the sun, or imagine trying to see through a thick bank of fog. In the early universe, matter existed not as the calm, neutral atoms we know, but as a searing plasma, a soup of bare atomic nuclei and free electrons torn apart by the heat. all of it packed together and crackling with energy. Light cannot move in a straight line through such a soup. Every time a ray of light set out, it almost immediately collided with a free electron and scattered off in a random new direction. Then it scattered again and again, ricocheting endlessly, never able to travel any real distance before being deflected once more. The universe was glowing white hot, but it was as impenetrable as the inside of a star. Light was trapped, bouncing forever in the fog, unable to escape, unable to carry any image, unable to reach anywhere at all. Then the universe did what it has been doing ever since. It expanded, and as it expanded, it cooled. The blinding heat of the beginning slowly faded as the cosmos grew larger, the temperature dropping century by century, millennium by millennium. And then, roughly 380,000 years after the beginning, the universe reached a critical temperature, around 3,000 degrees on the Kelvin scale, cool enough that something profound could finally happen. The free electrons, which had been racing through the plasma and scattering every ray of light, slowed enough to be captured by the atomic nuclei. Electrons and protons came together and joined into stable neutral atoms of hydrogen for the first time in the history of the universe. Physicists call this moment recombination, though in truth it was the first time the particles had ever combined at all. And in that moment, the fog lifted. With the free electrons swept up into neutral atoms, there was suddenly nothing left to scatter the light. The universe, in a span that was brief by cosmic standards, transformed from an opaque glowing plasma into a transparent and spacious cosmos, through which light could at last travel freely. For the first time, a ray of light could set out in a straight line and simply go on and on without being deflected. The universe became clear, and all the light that had been trapped in the fog for those first 380,000 years was suddenly released, free to stream across the newly transparent cosmos in every direction at once. This released light is the wall that Olbers imagined. Think carefully about what it looked like at that moment of release. The entire universe, everywhere in every direction, was glowing at a temperature of around 3,000 degrees Kelvin. That is the temperature of a dull, deep orange glow, like the surface of a fading ember or the heating element of a stove turned low. There was no dark sky then. If you could somehow have stood inside the universe at the moment of recombination, with eyes that could survive it, you would have seen the entire sky in every direction glowing a uniform, featureless, deep red, the whole cosmos shining like the inside of a vast warm furnace, with no gaps and no stars and no darkness anywhere. This is precisely the blazing, uniform, all-encompassing wall of light that Kepler feared and Olbers expected. It was real. The universe truly was once a sky of glowing matter surrounding every point, exactly as the paradox demanded. But that light was released almost 14 billion years ago, and it has been traveling toward us ever since, crossing an expanding universe the entire way. And we already know what an expanding universe does to light in flight. It stretches it. Over the nearly 14 billion years that this primordial glow has been traveling, the universe has expanded enormously, stretching the wavelength of that ancient light by a factor of about 1,100. The light that began as a deep orange glow at 3,000 degrees has been stretched and stretched until its wavelength is more than 1,000 times longer than when it set out. It has been redshifted out of the visible spectrum, past the infrared, all the way down into the microwave range. And as its wavelength stretched, its temperature dropped in exactly the same proportion, falling from around 3,000 degrees Kelvin to a frigid 2.7 degrees above absolute zero. This is the cosmic microwave background. It is the single most important and most beautiful confirmation of the Big Bang ever found. It is the afterglow of creation, the light released when the universe first became transparent, stretched and cooled by 14 billion years of cosmic expansion into a faint hiss of microwave radiation. And it is everywhere. It fills the entire sky, in every direction, with remarkable uniformity, a gentle uniform glow at 2.7 degrees Kelvin, coming from all sides at once. It is, quite literally, the wall of light that Olbers expected, surrounding us exactly as the paradox demanded, but cooled by the expansion of the universe until it is invisible to the human eye, detectable only by instruments tuned to the microwave band. Olbers was right. The sky is uniformly bright in every direction. We simply needed the right kind of eyes to see it. The story of how we discovered this glow is one of the most wonderful accidents in the history of science, and it deserves to be told slowly. In the year 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They had been given the use of a large, horn-shaped antenna, originally built to detect radio signals bounced off early communication satellites, and they intended to use it for careful measurements of faint radio sources in the sky. But to make those delicate measurements, they first had to account for every source of noise in their instrument, every faint hiss and crackle that might contaminate their data, and no matter what they did, they could not get rid of a persistent, faint background hiss. It was a small, steady signal, a low murmur of microwave noise that seemed to come from every direction in the sky equally. It did not change with the time of day. It did not change with the seasons. It did not point to any particular star or galaxy or region of the heavens. It was simply there, all the time, coming from everywhere, an even whisper of microwave energy that they could not explain and could not eliminate. They checked their equipment exhaustively. They suspected interference from the nearby city of New York. They suspected a fault in the antenna itself. And famously, they discovered that a pair of pigeons had nested inside the great horn of the antenna and coated its interior with droppings, a substance Penzias later described, with dry understatement, as a white dielectric material. They evicted the pigeons. They scrubbed the antenna clean. And still the hiss remained, faint and uniform and stubborn, coming from every direction in the sky. What Penzias and Wilson did not know was that, only a short distance away at Princeton University, a group of physicists led by Robert Dicke had been working out a remarkable prediction. They had reasoned that if the universe began in a hot, dense state, then the afterglow of that beginning should still be detectable today, stretched by the expansion into faint microwave radiation filling the entire sky. Dicke and his colleagues, including the young theorist Jim Peebles, were in fact in the process of building their own antenna to search for exactly this radiation. They were hunting for the very signal that Penzias and Wilson had already accidentally found and could not get rid of. The connection was made through a series of phone calls and a shared acquaintance, and when Dicke hung up the telephone after hearing Penzias describe the mysterious uniform hiss, he turned to his colleagues and said, simply, that they had been scooped. The two teams published their findings together in the year 1965, in adjoining papers in the same scientific journal. Penzias and Wilson reported the measurement of a strange excess of microwave noise, described in cautious, modest terms. Dicke and his group explained, in the companion paper, what that noise actually was. It was the light of the early universe. It was the afterglow of the Big Bang. It was the cooled and stretched remnant of the moment the cosmos became transparent. Two engineers trying to clean up their data had stumbled onto the oldest light in existence and had nearly dismissed it as the work of pigeons. For this discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in the year 1978. What almost no one remembers now is that this faint, stubborn hiss did far more than confirm a beautiful idea. It ended a war. For most of the middle of the 20th century, the question of whether the universe had a beginning at all was not settled science. It was a genuine and bitter dispute between two grand visions of the cosmos, two camps of brilliant people who looked at the same sky and the same equations and reached opposite conclusions. The hiss from that horn antenna in New Jersey was the evidence that finally tipped the balance, and to understand why it mattered so much, you have to understand what it defeated. On one side stood the idea we have been following all along, the notion that the universe began in a hot, dense state, and has been expanding and cooling ever since. On the other side stood a rival picture that was, in its own way, just as elegant, and to many minds far more comforting. It was called the steady-state theory, and it proposed something remarkable. It proposed that the universe had no beginning at all, that it had always existed, and would always exist, looking very much the same at every moment in its infinite past and its infinite future, not unchanging in its details, but unchanging in its overall character. A cosmos with no birth and no death, no fiery origin and no final darkness, simply enduring forever. The steady-state theory was put forward in the year 1948 by three physicists working in England. Two of them, Hermann Bondi and Thomas Gold, were Austrian-born scientists who had settled in Britain. The third was a Yorkshire-born astronomer named Fred Hoyle, a man of fierce intelligence and even fiercer stubbornness, who would become the theory's most famous and most relentless champion. Together they asked a daring question. What if the universe looks the same not only everywhere, but at every time? What if there is nothing special about the present moment, nothing special about any moment, and the cosmos has simply always been roughly as it is now? There was an immediate and obvious problem with this idea, and the steady-state theorists knew it perfectly well. The universe is expanding. The galaxies are flying apart. If space is stretching and the galaxies are thinning out, then the universe cannot look the same forever, because it must be growing emptier with every passing eon. A cosmos that is constantly diluting itself cannot be eternal and unchanging. The matter would simply spread out, thinner and thinner, until the universe was a barren and empty waste. To keep the cosmos looking the same while it expanded, the steady-state theory needed something extraordinary, and it proposed exactly that. It proposed that matter is continuously created out of nothing, not in a single violent beginning, but gradually, steadily, everywhere throughout all of space and all of time. As the galaxies drift apart and the space between them grows, the theory said, new atoms of hydrogen quietly come into existence in the emptiness, filling the gaps, providing the raw material for new galaxies to form in the widening voids. In this way, the universe could expand forever and yet never grow emptier, because the thinning was always balanced by fresh creation. The density of the cosmos would hold steady. The overall picture would never change. The universe would renew itself eternally, a little new matter at a time. And here is the detail that made the idea so difficult to dismiss. The rate of creation required was almost absurdly small. To keep the expanding universe at a constant density, you would need only about one single atom of hydrogen to appear in each volume of space the size of a large room, and not every year, but roughly once every few 100,000 years. This is a rate so slow, so utterly minuscule, that no experiment on Earth could ever hope to detect it. A few atoms drifting into existence across vast volumes of space over enormous spans of time. It was, in a sense, the gentlest possible form of creation, spread so thin across space and time that it would be entirely invisible. The steady-state theory asked you to believe in the continuous creation of matter from nothing, but it asked you to believe in it at a rate so small that you could never catch it happening. To many scientists in those years, this was a price well worth paying. The steady-state theory had a deep philosophical appeal. It required no beginning, and a universe with no beginning posed no awkward questions about what came before, no need to explain a first moment, no uncomfortable resemblance to old stories of creation. It offered a cosmos that simply was, eternally, governed by the same laws at every moment, with no special starting point that demanded explanation. For minds that found the idea of a sudden beginning troubling, whether for scientific or for deeper reasons, the steady-state universe was a refuge. It was orderly. It was eternal. It was, in its way, serene. Opposing this serene vision was the hot beginning, and its great champion was a Russian-born physicist named George Gamow, a brilliant and playful man who had emigrated to the United States and brought with him a powerful idea. Gamow reasoned that if the universe truly began in an unimaginably hot and dense state, then that early fire should have left a fingerprint, a trace of radiation that would still be present in the cosmos today. Working with his students, he set out to calculate what that trace should look like, and what they found would turn out to be one of the most prophetic predictions in the history of science, and one of the most thoroughly forgotten. In the year 1948, the same year the steady-state theory was published, two of Gamow's young collaborators, named Ralph Alpher and Robert Herman, worked through the physics of the cooling universe. They reasoned that the radiation released in the hot early cosmos would not have vanished. It would still be here, all around us, but stretched and cooled by billions of years of cosmic expansion until it had faded to a faint whisper. And they did something that the steady-state theory could never do. They put a number on it. They calculated that the leftover glow of the beginning should now fill all of space at a temperature of only about 5 degrees above absolute zero. A specific, concrete, testable prediction, made nearly 2 decades before anyone found the thing it predicted. And then, in one of the quiet tragedies of science, the prediction was forgotten. The radio technology of the late 1940s was not really capable of searching for such a faint and uniform signal, and so no one went looking. The calculation by Alpher and Herman was published, noticed by a few, and then slowly slipped out of the conversation. It sat in the scientific literature, correct and waiting, while the great debate raged on around it, with neither side fully realizing that the answer had already been written down. The prophecy had been made. The world had simply set it aside and moved on. Throughout the 1950s and into the 1960s, the two camps argued. The defenders of the hot beginning and the defenders of the eternal steady state each marshalled their evidence, each pointed to the weaknesses in the other's picture, and for a long while the matter genuinely hung in the balance. These were not cranks shouting past one another. They were among the finest scientific minds of their generation, and the question they were fighting over was as deep as any question can be. Did the universe have a beginning, or did it not? Was there a first moment, or had the cosmos simply always been? The honest truth was that, for a time, nobody could say for certain. The evidence was not yet decisive. The sky had not yet been made to speak. It was during this long argument that the most famous accident of naming in all of science took place. Fred Hoyle, the great champion of the eternal universe, was giving a series of talks on the radio for the British Broadcasting Corporation. In one of these broadcasts, near the end of the 1940s, he was describing the rival theory, the one that proposed a sudden fiery origin, and he reached for a vivid phrase to capture what he saw as its absurdity. He called it the idea that the universe began with a big bang. He meant it dismissively. He meant it as a way of making the theory sound crude. A single explosive moment, a cosmic blast standing in for serious physics. He was mocking it. But the phrase was unforgettable, and the mockery backfired in the most complete way imaginable. The name Big Bang escaped the laboratory and entered the language of the entire world. It became the name by which all of humanity would come to know the origin of the cosmos. The man who coined it did so in scorn, hoping to diminish the idea, and instead he gave it the one thing it had lacked, a name that anyone could remember. There is a strange justice in this. The deepest and most widely known fact about the history of the universe carries a name minted by the very person who spent his life arguing that it never happened. The skeptic named the thing he denied, and the name outlived his denial. Then came the year 1965, and the faint hiss in the horn antenna at Holmdel. When the measurement was understood, when the uniform microwave glow filling the sky was recognized for what it was, the long war effectively ended. Here was radiation coming from every direction, perfectly uniform, at a temperature of only a few degrees above absolute zero, precisely as the forgotten prediction of Alpher and Herman had described. The hot beginning had foretold this glow. The eternal steady state had not, and could not easily account for it, because a universe with no fiery origin has no reason to be filled everywhere with the cold remains of an ancient fire. The sky had finally spoken, and what it said was that the universe had a beginning. Most of the scientific community accepted the verdict. Over the following years, the steady-state theory faded from the mainstream, not because its defenders were foolish, but because the evidence had simply gone against them. The afterglow was real, it was everywhere, and its temperature matched the prediction of the rival camp almost exactly. The eternal universe, serene and beginningless, gave way to the universe with a birthday. The universe that had emerged from a hot, dense state nearly 14 billion years ago. The hiss that two engineers had tried so hard to scrub away had settled one of the oldest questions a human being can ask. And yet, in a final note that is almost unbearably human, the man who named the Big Bang never accepted that it happened. Fred Hoyle held to his belief in an eternal universe for the rest of his long life, refining his ideas, proposing modifications, searching always for some alternative to the beginning he could not bring himself to accept. He was a great scientist who made profound and lasting contributions to our understanding of how the elements are forged inside stars, work of genuine and enduring brilliance. But on this one question, the question of whether the cosmos had a beginning, the evidence left him behind, and he would not follow. He had given the beginning its name, and he went to his grave insisting there had been no beginning to name. The universe, for its part, kept no record of who had been right and who had been wrong. It simply was what it was, expanding and cooling exactly as it had been doing for billions of years, filled in every direction with the faint and patient glow of its own origin. The afterglow had been waiting all along, streaming silently through the long argument, through the radio broadcasts and the published papers and the forgotten prediction, indifferent to all of it, until at last someone built the right instrument and happened to listen. The answer had been written across the entire sky from the beginning. It only needed eyes that could read it. There is a detail here that brings the whole vast story down to something you may have touched with your own hands. In the era of old analog televisions, the kind with antennas that received broadcast signals through the air, if you turned the set to a channel with no station, you would see a screen full of dancing black and white speckles, that random visual snow, accompanied by a hiss of static. A small portion of that snow, a faint fraction of that random noise, was the cosmic microwave background itself, the afterglow of creation, picked up by the television antenna, along with all the ordinary static of the world. The light from 380,000 years after the birth of the universe was falling onto that screen in your living room, mixed into the snow. The beginning of everything was hissing quietly in the corner of the room, and almost no one knew to listen. And it does not stop at the television. The cosmic microwave background is passing through you right now. As you lie there in the dark, particles of light released when the universe first became transparent, nearly 14 billion years ago, are streaming through your body from every direction, thousands upon thousands of them passing through you every second, having travelled across almost the entire history of the cosmos to arrive at this moment. You are bathed constantly in the oldest light there is, the cooled remnant of the primordial fire. You cannot see it, you cannot feel it, but it is there, the whole sky glowing faintly around you in a colour your eyes were never built to perceive. In the decades since that accidental discovery, we have studied this ancient light with extraordinary care. Spacecraft launched specifically to map the cosmic microwave background have measured its temperature across the entire sky with breathtaking precision, and they have found it to be almost perfectly uniform, the same 2.7 degrees in every direction, to within tiny fractions of a degree. Those tiny variations, the faint ripples of slightly warmer and slightly cooler regions, are themselves precious beyond measure, because they are the seeds of everything. The slightly denser regions in that ancient glow were the places where gravity would later pull matter together to form the first galaxies, the first stars, and eventually the planets and the people that came after. In that faint pattern of warmth and cool, frozen into the oldest light, we can read the blueprint of the cosmos we live in. The wall of light that Olbers expected to find did not just confirm that the universe had a beginning. It carried within it the very pattern from which all the structure of the universe, including us, would grow. So return now to the darkness of the night sky and see how completely it has been transformed. It is dark, to our eyes, because the universe has a finite age, which limits how far we can see and cuts off the supply of distant starlight at a horizon made of time. It is dark because the expansion of space stretches the light of the most distant sources, draining its energy and shifting it out of the colours our eyes can perceive. And the great uniform wall of light that the old paradox insisted must surround us, the blazing sky that should be there, genuinely is there, exactly as predicted. But it has been cooled and reddened by the expansion of the universe from a blinding orange glow into invisible microwaves at 2.7 degrees above absolute zero. The night sky is not truly dark. It only looks dark to creatures whose eyes evolved to see a narrow band of colours. In the microwave light we cannot see, the entire sky is glowing, uniformly, in every direction, with the afterglow of the moment the universe was born. There is a part of this story that is almost always left out, and it may be the most quietly astonishing part of all, because it is the chapter in which the night sky was darker than it has ever been since. We have followed the universe to the moment it became transparent, the moment the fog of plasma cleared, and the light streamed free across space for the first time. It is tempting to imagine that this was a moment of brightening, a sky suddenly filled with light, but the truth is almost the opposite. When the fog cleared, the glow was already fading, and what came next was not light, but darkness. A long, deep, total darkness, unlike anything the cosmos would ever know again. Consider the universe in the years just after recombination. The great glow of the hot early cosmos, that deep orange light filling all of space, was cooling and dimming as the universe expanded, sliding down through the colours toward red and then toward the invisible. Within a relatively short span of cosmic time, that primordial light faded out of the range any eye could see, leaving the universe filled with nothing but cold, dark, neutral hydrogen gas, drifting in an immense and growing blackness. And crucially, there were no stars. Not a single one. Not one point of light anywhere in all of existence. The stars had not yet been born. This is the era that astronomers call the cosmic dark ages, and the name is not a metaphor. It is a plain description. For a stretch of time lasting somewhere between 100 million and 200 million years, and perhaps longer, the entire universe was genuinely completely dark. No stars, no galaxies, no glowing points scattered across the heavens. Only vast clouds of cold hydrogen and helium, spread thin through an expanding void, with the last embers of the afterglow stretched far beyond the reach of any vision. If you could have opened your eyes anywhere in the cosmos during those long ages, you would have seen nothing at all. Not darkness scattered with distant lights, as on the clearest night you have ever known. Simply darkness, total and unbroken, in every direction, with nothing anywhere to break it. And here is the thought worth holding on to, the one that turns this whole long meditation back upon itself. We began by asking why the night sky is dark. We have spent these hours uncovering the reasons: the finite age, the stretching of light, the cooling of the ancient fire. But there was once a time when the sky was not merely dark to human eyes, but dark in the most absolute sense that has ever existed. Dark because there was, quite simply, nothing yet lit. The darkness did not come after the light, as a fading or a loss. The darkness came first. The light is the newcomer. Every star you have ever seen, every galaxy, every candle and every fire, all of it came later, kindled out of an original blackness that filled the young universe from edge to edge. Before there was light, there was the dark, and the dark was patient. But the darkness was not empty, and it was not still. Woven invisibly through all that cold hydrogen was the faint pattern we spoke of earlier, the gentle ripples frozen into the ancient glow, the regions that were very slightly denser than their surroundings. These differences were almost nothing, variations of a tiny fraction in the smoothness of the gas. But gravity does not need much to begin its work. and gravity does not grow tired. In the slightly denser regions, the pull was very slightly stronger, and so a little more gas drifted inward, which made those regions denser still, which strengthened the pull a little more. Slowly, across millions upon millions of years, in the silent dark, the gas began to gather. The denser knots drew in their surroundings, growing heavier and more concentrated, the hydrogen falling inward and warming as it fell, the temperature climbing at the heart of each gathering cloud. And then, somewhere in that vast blackness, for the first time in the entire history of the universe, something extraordinary happened. At the center of one collapsing cloud of hydrogen, the gas grew so dense and so hot that its core reached the temperature at which nuclear fusion ignites. Atomic nuclei began to fuse together, releasing energy, and a sustained light kicked on in the darkness. A star had been born. The very first star, the first object in all of existence to shine by its own power, the first true light in a cosmos that had known nothing but blackness for 100 million years and more. After the long dark, a single point of brilliance, and then another, flickering on across the void. Astronomers call this turning point the cosmic dawn, and it is one of the most profound moments in the history of everything. These first stars were not like the gentle, long-lived stars that fill the sky tonight. They were born from gas that contained almost nothing but hydrogen and helium, the simple elements forged in the first minutes of the universe, with none of the heavier ingredients that later stars would have. Lacking those heavier elements, the first stars grew to colossal sizes, many of them tens or even hundreds of times the mass of our Sun. They burned a fierce blue-white, prodigiously hot and almost violently bright, and they lived fast and died young, consuming their fuel in just a few million years before ending their brief and brilliant lives. And the way they died mattered as much as the way they lived. Many of these first great stars ended in tremendous explosions, the deaths of massive stars, blasts of such ferocity that in their final moments they forged the heavier elements that the early universe had lacked. In the cores of these stars and in the fury of their explosions, hydrogen and helium were fused and transformed into carbon, into oxygen, into nitrogen and silicon and iron, the heavier atoms that had never existed before. And those explosions flung the newly made elements outward into space, seeding the surrounding gas with the raw material of everything that was to come. The first stars lived briefly, died violently, and in dying they enriched the cosmos with the very substances from which planets and oceans and living bodies would one day be assembled. This is not a poetic flourish. It is literal, physical fact. The carbon in your cells, the oxygen filling your lungs as you breathe slowly in the dark, the iron carried in your blood, the calcium in your bones. Every one of these atoms was forged inside a star, many of them in the generations of stars that traced their lineage back to those first great fires that ended the cosmic dark ages. You are, in the most precise and unsentimental sense, made of the ashes of dead stars. The darkness ended when the first stars lit themselves, and the deaths of those stars sowed the universe with the dust from which you eventually were made. As the ages passed, more and more stars ignited, and they gathered together under gravity into the first small galaxies, which merged and grew into larger ones. The cosmos that had been uniformly dark began to fill with islands of light, and the fierce radiation pouring out of all these new stars did something to the cold hydrogen gas that still filled the spaces between. The energetic light from the first stars and galaxies tore the electrons back off the neutral hydrogen atoms, stripping them apart again, ionizing the gas across vast stretches of space in an era that astronomers call the reionization of the universe. The fog of neutral hydrogen that had filled the dark ages was gradually burned away by starlight, cleared and thinned, until space became fully transparent to starlight in the way we know it tonight. The universe had remade itself once more, from a dark sea of neutral gas into a luminous web of stars and galaxies shining across a transparent void. So the night sky that you gaze up into now, scattered with its thousands of visible stars, and beyond them, its billions upon billions of unseen ones, is the end product of that long and patient climb out of an original darkness. There was the fire of the beginning. Then the fire faded, and there was the great dark. Then, in the dark, gravity gathered the gas, and the first stars caught light, and the cosmic dawn broke across the universe. And from that dawn flowed everything that came after: the galaxies, the later stars, the planets, and on at least one small world circling one ordinary star, the slow emergence of creatures who could look up at the result and wonder why the spaces between the lights are dark. And here is something remarkable. We are no longer limited to reasoning about the cosmic dawn from theory alone. In recent years, we have begun to actually see it. Because light takes time to cross the vast distances of space. To look far across the universe is to look backward in time. The most distant galaxies we can detect lie so far away that their light has been travelling toward us for more than 13 billion years, which means we do not see them as they are now. We see them as they were when the cosmos was young, only a few 100 million years after the beginning, near the very end of the Dark Ages and the first light of the dawn. The light from those early galaxies has been stretched so severely by the expansion of the universe that it has slid entirely out of the visible range and deep into the infrared, the band of light we feel as warmth rather than see as colour. To gather it, astronomers built an instrument designed for precisely this task, the James Webb Space Telescope, launched at the very end of the year 2021 and stationed far out in space beyond the orbit of the Moon. With a great golden mirror tuned to collect faint infrared light, it was built to peer further back toward the beginning than any eye before it. And what it found has surprised even the scientists who made it. Looking back toward the cosmic dawn, it has revealed galaxies that already existed only a few 100 million years after the beginning, some of them larger and brighter and more fully formed than anyone had expected to find so early. The first chapters of cosmic history, hidden for so long, are now being read directly from the sky, and they are forcing astronomers to reconsider just how quickly the great darkness gave way to light. There is an even deeper frontier still being pursued. The cosmic dark ages themselves, the long stretch before any star had formed, left a faint signature behind. The cold neutral hydrogen that filled the young universe absorbed and emitted radio waves at one very particular wavelength, and that ancient signal, stretched by billions of years of expansion into much longer waves, may still be faintly detectable today. Around the world, astronomers are constructing sensitive radio instruments to try to catch this whisper, to listen, in effect, to the silence that reigned before the first stars. If they succeed, we will hold a direct record of the universe's darkest age, the long night that came before the dawn. We are learning, slowly and patiently, to look all the way back to the boundary between the original dark and the first light. But hold one final thought as we prepare to follow this story to its very end. The age of starlight that we live in now, this era of a sky full of shining suns, is not the permanent condition of the universe. It is a phase. It had a beginning, at the cosmic dawn, and it will have an end. For the stars are not eternal. Each one burns through the fuel it was born with, and when that fuel is exhausted, the star dies. And unlike in that old dream of an eternal and self-renewing cosmos, there is no steady creation of fresh matter to replace what is spent. The supply of gas from which new stars can form is finite, and across the long reaches of future time it is slowly being used up. The darkness came before the stars, and in the deep future, after the stars, the darkness will come again. There is one more turn in this story, and it is the darkest of all, because it reaches not into the past, but into the future. We have learned that the night sky is dark because the universe is finite in age and stretched by expansion. But that expansion is not holding steady, and it is not slowing down. It is speeding up. And as it speeds up, the darkness that surrounds us tonight is going to deepen, slowly and inexorably, until the universe becomes a far emptier and far lonelier place than it is now. The sky is not only dark, it is getting darker. For most of the 20th century, astronomers assumed that the expansion of the universe must be gradually slowing down. This seemed obvious. All the matter in the cosmos pulls on all the other matter through gravity, and that mutual pull should act as a brake on the expansion, slowing it over time, the way a ball thrown upward is slowed by the gravity of the Earth. The only real question, it seemed, was whether gravity was strong enough to eventually halt the expansion and pull everything back together, or whether the universe would simply coast outward forever, slowing but never quite stopping. Nobody seriously imagined a third possibility. Then, in the year 1998, two competing teams of astronomers set out to measure precisely how much the expansion was slowing. They used a special kind of exploding star, a type of supernova that always detonates with very nearly the same true brightness, making it a reliable cosmic measuring stick. A standard candle visible across enormous distances. By measuring how bright these distant supernovae appeared, the teams could work out how far away they were, and by measuring their redshift, they could work out how fast the universe had been expanding when the light left them. They expected to find the expansion gently decelerating. Instead, both teams found the opposite, and the result was so strange that each of them spent months trying to find the mistake before daring to believe it. The distant supernovae were fainter than they should have been. The expansion of the universe was not slowing down at all. It was accelerating. Something was pushing the cosmos apart, overcoming the inward pull of all its gravity, and driving the galaxies away from one another faster and faster with every passing eon. We do not know what this something is. We have given it a name, dark energy, but the name is little more than a label for our ignorance. It appears to be a property of empty space itself, a faint pressure woven into the vacuum, pushing outward everywhere at once, growing in total influence as the universe grows larger and there is more empty space to do the pushing. The honest answer is that nobody truly knows what dark energy is, and it stands today as one of the deepest unsolved mysteries in all of science. But whatever it is, its effect on the future of the cosmos is clear, and it is sobering. The acceleration will continue. The galaxies will be driven apart ever faster, and the consequences for the night sky across the immense stretches of future time are profound. Consider what an accelerating expansion does over billions and trillions of years. Right now, our own galaxy, the Milky Way, belongs to a small gathering of galaxies bound together by gravity, including the Great Galaxy in Andromeda and a few dozen smaller companions. This local group is held together tightly enough that the expansion cannot pull it apart. In fact, Andromeda and the Milky Way are drifting toward each other, and in roughly 4 billion years the two great spirals will collide and merge into a single larger galaxy. That much gravity will keep close. But everything beyond our local group is a different story. Every other galaxy in the universe, the hundreds of billions of them scattered across the observable cosmos, is being carried away by the accelerating expansion, receding faster and faster, slipping toward that horizon beyond which their light can no longer reach us. Now extend that across deep time. As the expansion accelerates, more and more distant galaxies will cross the cosmic horizon, their recession outrunning the light they emit, until one by one they vanish from view, not by moving out of sight in any ordinary way, but because the space between us and them grows faster than their light can cross it. In the far future, perhaps 100 billion years from now, an astronomer in our merged galaxy will look out into the cosmos and see nothing beyond their own island of stars. Every other galaxy will have receded beyond the horizon, its light forever cut off, the sky beyond the local group utterly and permanently empty. The rich cosmos of countless galaxies that we can see tonight will have disappeared, leaving a single galaxy alone in an ocean of perfect blackness, with no visible evidence that anything else ever existed. And here is the cruelest part. That future astronomer would have no way of knowing the truth. The cosmic microwave background, the afterglow of the Big Bang that surrounds us today and reveals the universe's hot beginning, will itself be stretched by the continuing expansion until its wavelength grows longer than the size of the observable universe, fading until it can no longer be detected at all. The distant galaxies whose redshifts revealed the expansion to Hubble will be gone, vanished beyond the horizon. The future astronomer, studying a single isolated galaxy in an apparently empty and unchanging void, with no distant galaxies to observe and no afterglow to detect, would have every reason to conclude that the universe is static, eternal, and consists of nothing but their own island of stars. They would arrive, through honest observation, at exactly the picture of the cosmos that Kepler and Olbers held, the very picture we now know to be false. The evidence of the Big Bang, the evidence of the expansion, the evidence of the vast and ancient cosmos, will all have been carried away by the expansion itself. The universe will have erased the story of its own origin. This is a genuinely staggering thought. We happen to live in a privileged window of cosmic time, an era in which the universe is still young enough and full enough that we can look out and read its history, written in the light of distant galaxies and the glow of the cosmic background. We can see the expansion, we can detect the afterglow, we can know that there was a beginning, but this window is closing. The same expansion that keeps our night sky dark is also slowly carrying away all the evidence of how the universe came to be, and in the far future, the cosmos will fall silent and dark and apparently eternal, its origins hidden forever from any who come after. We are among the fortunate few who get to live while the universe still remembers its own birth, and it goes further still, into a future almost too vast to contemplate. Long after the distant galaxies have vanished, the stars themselves will begin to fade. Stars form from clouds of gas, and the supply of fresh gas is finite. As the eons pass, the gas will be used up, and fewer new stars will be born. The existing stars will burn through their fuel and die, the brilliant ones first, then the long-lived dim ones, over spans of time that dwarf the entire history of the universe so far. Eventually, across timescales with so many zeros that the numbers lose all meaning, the last star will flicker and go out. The galaxies will become dark graveyards of stellar remnants, cooling cinders and dead embers drifting in the black. And the universe will settle toward a final state of cold, formless, featureless darkness, every fire extinguished, every source of light exhausted, an endless night with nothing left to break it. Physicists call this the heat death of the universe, the ultimate triumph of the cold and the dark over the warm and the bright. So the darkness of the night sky, which began as a simple puzzle, has led us all the way to the end of time. The sky is dark tonight because the universe is young enough to be mostly empty between its scattered fires and old enough that those fires have not had time to fill it. But in the deepest sense, the darkness is winning. It was there before the first star ignited, and it will be there after the last star dies. The light is a brief interruption, a temporary glow in a cosmos that begins in darkness and ends in darkness. And the black between the stars that you see tonight is a small foreshadowing of the final and permanent darkness, toward which everything is slowly, patiently moving. And yet, even knowing all of this, even standing at the edge of that final cold, there is something here that is not despair. There is something in this vast and indifferent cosmos that leaves room, after all, for warmth, and for meaning, and for the strange privilege of being here at all to understand it. Because step back now from the physics, from the shells and the redshifts and the afterglow, and consider the simple, almost unbearable fact of your own position in all of this. You exist in a universe that stretches at least 93 billion light-years across in its observable extent alone, filled with 200 billion trillion stars, born nearly 14 billion years ago, and racing toward an end so distant that the numbers describing it cannot be felt. You are a brief arrangement of atoms, gathered together for a flicker of cosmic time on the surface of a small wet rock orbiting an ordinary star, in the outskirts of one galaxy among countless others, most of which you will never see, and which are even now slipping away beyond your reach. By every measure of size and time and permanence, you are almost nothing at all, a speck, on a speck for an instant. And perhaps that should feel crushing. Perhaps the proper response to a universe this vast and this indifferent, a universe that begins in darkness and ends in darkness, and will one day forget that you or your entire species ever existed, is a kind of quiet despair. Perhaps the darkness overhead is a reminder of how little we matter, how briefly we last, how completely the cold will win in the end. That reading is available. It is not foolish. The facts genuinely point that way. Or perhaps it is something else entirely. Perhaps the more remarkable truth is this: in all that vastness, across all that time, in a cosmos overwhelmingly composed of empty space and cold darkness and indifferent physical law, a small portion of the universe has arranged itself into something that can look up at the rest of it and understand. You are the universe become aware of itself. The same atoms that were forged in the hearts of dying stars, the same matter that was once part of that primordial fire whose afterglow still surrounds us, has assembled itself, here, into a mind capable of asking why the night sky is dark, and patient enough to follow the answer across 400 years and 14 billion light years to its source. The cosmos is mostly dark, and mostly empty, and mostly cold. But it is not entirely so. Not here. Not now. Not in this brief and luminous window, when there are stars to see and eyes to see them, and minds to wonder what it all means. These are not questions that science can answer for you, whether the vastness should make you feel small and afraid or small and grateful, whether the coming darkness should fill you with despair or with a fierce tenderness for the light while it lasts. Different people, looking up at the same dark sky, will feel different things, and there is no single correct way to feel beneath it. The universe hands you the facts. What you make of them, what meaning you find in your brief flicker of awareness inside the long cosmic night, is yours alone to decide. But consider, as you drift towards sleep, what the darkness has actually given us. For thousands of years, people looked up at the black between the stars and saw nothing but the ordinary absence of the sun. They could not have guessed that the darkness itself was a message, that it held within it the secret of the universe's age, the proof of its expansion, the evidence of its fiery birth, and the foreshadowing of its distant end. The darkness was never empty. It was full of meaning, waiting patiently for minds curious enough and careful enough to read it. The blackness overhead is not a void. It is the oldest and deepest story there is, written across the entire sky, telling us where everything came from and where it is all going. So the next time you step outside on a clear night and tilt your head back into the dark, remember what you are truly looking at. You are not looking at nothing. You are looking back through time, toward the edge of the visible universe, toward the very beginning of everything. You are bathed, in that moment, in the cold light of creation, glowing faintly all around you in a color you cannot see. And you are witnessing, in the simple darkness between the stars, the answer to a question that took humanity 4 centuries to understand. The sky is dark because the universe was born, because it is growing, and because the light has not had time to fill it. The darkness is not the absence of an answer,